Welcome to This Explainer. We've designed this specifically for IT students who want to master monitoring and control systems and, honestly, absolutely crush their next exam. So, if you've been struggling to piece together exactly how sensors, microprocessors, and actuators actually work out there in the real world, well, you are in exactly the right place.
Let me ask you a quick question. Are you losing easy marks on your IT exams simply by confusing monitoring with control? Because it's literally the ultimate student pain point. We see so many students lose marks because they write these kind of vague answers that mix up two entirely different foundational concepts. So let's just dive right in, clear up the confusion once and for all, and lock in those top band marks.
All right, Section 1, Monitoring versus Control Systems. Let's get straight to a totally jargon-free breakdown of how these two actually differ.
So the absolute core of the difference comes down to the output. A monitoring system simply watches and records data. It processes data so humans can spot trends or maybe get an alert if something goes wrong. Think of a weather station just passively recording rainfall, or a hospital alarm that goes off when a patient's heart rate drops. But control systems, they are a whole different beast. In a control system, the output actually affects the input. The microprocessor processes the data and makes a hard decision to take physical action, like turning on a heater. And doing that actually changes the temperature being monitored. It's a continuous active loop of sensing and acting.
Moving right along to Section 2, Sensors and System Calibration. Let's talk about the eyes and ears of our computer systems.
What is a sensor? Basically, it's a device that collects continuous data representing physical changes in our environment. Now, notice how I emphasize the word continuous. A massive misconception is that sensors only send data when something changes, or maybe every few minutes. Nope. They are constantly feeding data to the microprocessor, the system's brain. But there's a little catch. Our physical world is analog, right? But the computer's brain is strictly digital. So that continuous stream of analog data has to pass through an ADC, an analog to digital converter, before the microprocessor can even understand it.
There are tons of different sensors out there, and you absolutely need to know which ones fit specific exam scenarios. Light sensors, for instance, pop up in weather stations or when measuring river pollution. Temperature sensors are your go-to for air quality or climate control. Pressure sensors monitor atmospheric pressure, and pH sensors are perfect for measuring acidity in soil or a river. Definitely lock these examples in your memory. They're going to be your best friends when an exam throws a random real-world scenario your way.
Now you might be thinking, hey, it's a computer system, it's got to be 100% accurate forever, right? Well, not exactly. Sensors actually deteriorate over time because of regular wear and tear and just being exposed to the elements. So, to stop their accuracy from drifting off, they have to be regularly calibrated against a known standard value. We can visualize this process using calibration graphs. Sometimes it's a super simple linear adjustment, basically just adding a fixed offset across a straight two-point graph. But other times, say for things like cooling liquids, the relationship isn't a straight line at all, which means we have to use a nonlinear, multi-point calibration curve to keep things accurate.
Okay, Section 3, Actuators, making things move. We know how the system's brain gathers info. Now let's see how it actually gets things done using its hands and muscles. In plain English, actuators are the physical outputs in a control system that do the heavy lifting. They're devices that take an electrical signal from the microprocessor and turn it into real physical movement. So if the microprocessor decides a room is too cold, the actuator is the actual physical part that opens up a valve to let hot water rush into a radiator.
A really common example of this is the linear solenoid actuator. Think of it as an electrical coil wound tightly around a tube that has a plunger inside. When the computer sends an electrical current through that coil, it generates a magnetic field, and depending on the polarity, it either attracts or repels that plunger in a simple straight line, just pushing or pulling. That straight line, linear motion, is absolutely perfect for doing things like unlocking doors or flipping heavy electrical switches.
But what happens if you need something to spin? For rotational movement, we use something like a rack and pinion mechanism. Imagine a flat bar with teeth. That's the rack. As it pushes forward in a straight line, those teeth lock into a round gear called a pinion, forcing it to spin. Or you can run the whole thing in reverse, turning spinning motion back into straight line motion. This kind of mechanical rotary actuator is absolutely crucial for complex tasks, like moving the joints of a robotic arm in an automated car factory.
All right, let's bring this all together in Section 4, Real-World System Applications. We've got our inputs and outputs. Let's see the complete loop in action.
This right here is the core logic loop you must memorize. Step 1, input the digital data from your sensor. Step 2, the microprocessor compares that data against a preset value that a human originally typed in. Step 3, if that reading is outside the acceptable range, the microprocessor fires off a signal to an actuator to fix it. And Step 4, the whole entire process repeats, continuously, non-stop, in real time.
Let's actually map that 4-step logic onto an automated greenhouse. Let's say we want to maintain perfect soil moisture. The farmer inputs a preset value. Down in the dirt, the moisture sensor is constantly sending out analog data, which our handy ADC changes into digital. The microprocessor compares it. If the dirt is getting too dry, it sends an electrical signal straight to the actuator to crank open the sprinkler valve. Once the moisture rises back up to the preset level, the next rapid-fire loop of the algorithm catches it. The microprocessor updates its decision and sends a new signal to close the valve. It's a brilliant, totally self-correcting loop.
Now, exam papers absolutely love to test this logic using flowcharts. For instance, consider the processing for a central heating system. The key part is the decision diamond. Is the temperature less than the preset? If yes, you follow the path that sends a signal to open the valves and fire up the pump. If no, you follow the path to close the valves and shut the pump off. And notice how the arrow loops right back up to the top. Visualizing this exact step-by-step flow in your head is seriously your secret weapon for writing flawless exam answers.
Which brings us nicely to Section 5, Master the Exam Strategy. Let's take all this cool tech theory and turn it into solid marks.
Before you write a single word in the exam hall, you have to run a diagnostic check. You must identify the command word. Is the question asking you to define, describe, explain, analyze, or evaluate? Because guys, each of those requires a totally different depth of response. Also, watch out for the common pitfalls. The big ones are concept confusion, like accidentally mixing up our monitoring and control definitions, and vague theory, which is when you write a generic textbook answer that completely ignores the specific scenario the question actually gave you. So how do we actually cure vague theory? We use the PLJ framework. A weak 3 out of 10 answer is just generic and imprecise. But to build a top band 9 out of 10 response, here is your cheat code. P stands for point. State your technical claim using proper syllabus terms. E is for evidence. Pull specific data directly from the scenario they gave you. The second E is elaborate. Explain the sequence of operations. Literally just write out that step-by-step algorithm loop we just learned. L is for link. Connect it back to the practical consequence for the business or person in the scenario. And for those absolute top-tier marks, J is judgment. Provide a quick comparative evaluation of why this method is better or worse than an alternative.
To wrap things up, I want to leave you with a quick brain teaser to test what you've learned today. Think about an automated farm irrigation system. It relies on high-tech sensors to measure soil moisture. But when the alarm goes off, it requires a human farmer to physically walk out into the field and crank the water valve open. So is that a monitoring system or a control system? Think back to what we said earlier about the output affecting the input without any human intervention. All right, that is a wrap for this explainer. Keep practicing those PLJ responses, always visualize your system loops, and I'll see you in the next one.